Thank you very much for that excellent introduction, because it sort of covers exactly what it is that we're going to talk about today. A little bit about collagen and ice templating, and a little bit about the electroactive sides. So hello everyone, once again thank you for introducing me. My name is Malavika, and today I would like to talk a little bit about how we can use biomaterials, particularly electroactive biomaterials, to create what I like to call smart biomedical devices. So what are medical devices to start with? I'm sure we're all familiar with a range of these different items. We've seen them around, not just in optometrists and in any of the medical pharmacies, but also lying around the house, like a pair of gloves, and also, more simple things like a Band-Aid. But when we think of medical devices, it tends not to be these very, very simple devices that comes to our mind. It tends to be the much more sophisticated ideas, such as the pacemakers or the prosthetic arms with robotic functionality. So one way in which I like to categorize these different devices is by putting them on a scale of biomimicry, so learning from nature, and biocompatibility. So as an example, if we were to look at the lenses that you would test, 1 or 2, at the optometrist, then you would know that this is something that hopefully needs to mimic healthy eyes as well as possible, but it doesn't need to be particularly compatible with our body. We're not interfacing with it for a very long time. On the other hand, something like rubber gloves that we'd wear for our protection should really not be mimicking our hands very much, otherwise there's not much point in wearing them. So we should be having a protective layer over our hands, but they should be biocompatible regardless, so we don't want to get any allergies as a result of wearing them. So some of these more complicated, sophisticated devices that we think of tend to be in this upper right-hand quadrant of this diagram. So they tend to be the ones that display the highest levels of biomimicry, but also the highest levels of biocompatibility. But if I were to ask, what would be the ideal device? The ideal device to me would be one that is, of course, got a hokey acronym, a smart device. A device that is capable of being sensing, of modulating tissue, of actuating, so that is to say it can move and generate energy, regenerate tissue, and can also have a therapeutic effect. I would argue that actually the most biocompatible and the most biomimicking thing that is out there is actually our organs and tissues themselves. So they would actually sit in the upper right-handmost quadrant of this diagram, where they show excellent biomimicry and excellent biocompatibility. So how can we then learn from what we already know from these different tissues and organs to hopefully implement within the lab so that we can modify these different elements for the medical devices of our interest? Luckily for us, there is one common element across the majority of the tissues that we see. So whether it's the lung, the cornea, muscle, heart, tendons, ligaments, and even a tiny little bit of the brain, they all have this loose connective tissue, this extracellular matrix that surrounds the cells. And the major protein in all of this is a little triple helical molecule called collagen. Definitely not biased, definitely not my favorite protein, but it is what we will be using as the base material because it is so commonly found within our bodies. So what we can do with this collagen is to try to create a scaffold for tissue engineering. And that's where we start on this journey of regenerative biomaterials. I've just put a little picture of a frog here because a lot of reptiles have a lot of innate capability to regenerate themselves. That's not something we quite have in ourselves. Our skin does regenerate quite quickly in about 7 days, but other organs such as the heart or the bone can take up to 20 years in healthy tissue. So what can we learn from what these different systems have, and how can we build scaffolds for tissue regeneration? So hopefully, as you've seen here, there's a nice little picture of a construction worker around some scaffolds, and that should be nothing that's too unfamiliar for all of you. They're just scaffolds all around various dilapidated buildings here in Oxford, and their main purpose is to essentially be a delivery vehicle for the construction workers to the site of repair. They're temporary constructs. They're there while the repair work is being done, but they come down at the end of the repair work. And they provide structural support while the repair is being done. The only difference between a scaffold for construction work and a scaffold for tissue regeneration is that the construction workers are replaced by cells. So the cells either within the body or the ones that we put specifically in these constructs are the essential components, the essential agents that we try to deliver to allow the regeneration to occur on its own. So there is one key element that we haven't talked about, and that is what we would make these scaffolds out of. So here you see this little spongy structure, and it needs to also mimic the tissue microenvironment. That is one condition that is quite different between a scaffold for tissue engineering versus just the scaffolds that we see with steel girders outside. So it needs to be able to mimic the tissue microenvironment in order for us to be able to replicate our tissues of interest. So we have one protein that we've talked about, collagen, but there's many different tissues. And you can see that just having that one protein alone doesn't really make for homogeneity in the behavior of these tissues. So up in the top left, we have some skin, moving on to tendon and muscle, and the heart muscle in the bottom right. They all have different structures, and they all have different functions as a result of their different structures across the length scale. So it's well and good to say that it's made out of collagen, but actually they are arranged in very different ways, and they make the cells behave in very different ways as a result as well. So in short, one way to say this is that cells respond to structure, not just in one length scale, but across the length scale. Starting from the left-hand side, we have the micro scale, where we have the cells that use the empty space within these extracellular matrices to move through and migrate and respond to other chemical cues and electrical or mechanical cues that are provided within the structure. It also responds to topography. It likes to, much like the bacteria sticking to the walls, our cells also like to stick onto anything that it can grab onto. And of course, it recognizes very specific molecular cues as we go further down the scale. So the question is, how can we try and replicate some of these structural features such that we can actually try to mimic the tissues that we're trying to regenerate as closely as possible? So to replicate our tissue structures, in the lab we follow a process where we start with our collagen. This is essentially a slurry. It's blended up collagen. It's a liquid. But we need to end up with something that looks a little bit like a sponge. So it's a little cake in a 6-well plate. But it's not okay for it to just be that cake. It also has to have an internal structure that is porous and interconnected to allow the cells to move from one end to the other end. So how do we achieve this? So this is where some of the ice that was introduced earlier comes into play. So the way in which we create these scaffolds is through a process known as ice templating. So what we do here is we start essentially with a solution, or a suspension, I should say, of beef and vinegar. So a collagen slurry, where we have all these collagen molecules floating around in a sea of water. If we were to take this, we can freeze the suspension. And what that allows us to do is have ice crystals that form within the suspension. Now, solid H2O, ice, is particularly intolerant to the incorporation of other solutes into its crystal structure. So when it forms ice, it will tend to reject everything else that's around it towards the boundaries of the growing ice crystals. So in other words, it is essentially templating the collagen to form around the growing ice crystals. So we need a way to get rid of the ice. Unfortunately, if we just take it all the way back down and melt it, we'll just get a suspension again. So we instead drop the pressure and allow the ice to sublime, which gives us essentially this porous, interconnected scaffold that allows the cells to move from one end to the other. So this is all well and good, but it's not enough. How else can we use some of this information to make better structures, to try and create aligned structures or structures that are a little bit more random? Well, we can bioprint some of these structures, and in some ways, if we've started also printing them directly onto a cold plate, so we can start to engineer and fabricate these structures to be bespoke, to fit exactly what it is that our final structure should look like. But more importantly, the internal structure can be predicted quite often using a bit of modeling of the thermal fields during the freezing process, and also the sublimation process. In this particular example, one of our students has modeled the flow of the heat out of the mold that she's created to try and create the aligned pore structures that you see on the top right, mimicking a little bit more what the heart structure looks like, rather than on the bottom right, where you have the more open and more rounded pores that you would tend to see in a tissue like skin. So this is all well and good. We do have our regenerative scaffolds all set up, ready to be put into our various applications, but there are still limitations. There is no dynamic monitoring or control of the cellular behavior, the material degradation or the material mechanics. So we measure these things in the lab, we say this is exactly how it works, and then that's it. We just hope for the best and hope this is exactly how they're going to behave when they're put into a patient, or, I mean, it's not quite out there for clinical use for some of these things, but that's our hope. There's no way really of controlling or measuring these things. So this is where the second half of this presentation comes into play, which is the introduction of electroactive biomaterials. So the one thing about introducing electronics into most systems is that it gives us the ability to start sensing and monitoring and recording a lot of data. But making electronics based out of the extracellular matrix, or the ECM for short, is actually quite difficult. So conventional electrodes for stimulators, so if we were to try and create electrodes to stimulate, whether it's a particular, we're trying to either record information or send signals to stimulate a particular device, they tend to have issues because there is very poor integration with the tissue. Often, if you've ever had the misfortune of having a splinter, you will know that after a while it starts to work its way out. It's pretty much the same thing. If you try and insert a foreign body into your brain or into some other tissue, it would isolate itself, and there's very poor integration with the tissue of interest. And that means that often when you're stimulating, you need a higher injection current. You need a higher than normal current that you need to put through in order to achieve the desired therapeutic effect for stimulation. Now, we can use extracellular matrix materials, such as collagen, but the problem is they're really not conductive. In fact, they're so not conductive that the conductivity of insulating materials, such as Kapton, polyamide, tends to dominate over that of collagen. So we need to find a way to let the two marry together and have a better way of introducing some of this electronic or ionic conductivity into these structures. So one way we can achieve that is through simple hybridization, so simple co-printing of metallic particles such that we can get nice interconnected structures that are electrically conductive. So here we have an example of collagen that has been printed on its own and collagen that has been printed with silver, showing only 2 to 3 times the resistivity of printed silver. For some context, the conductivity of collagen is about 8 orders of magnitude different from that of pure silver. So having something that's just 2 to 3 times is actually a compromise that we're very willing to take over these several orders of magnitude that we lose. However, there is another way we can approach this. So going back to the picture of the structure, we can look at what happens at the nano and molecular scale to look at the structure of collagen. So if we were to modify some of these biochemical and electromechanical cues, it might be that we can start to introduce a little bit more of electrical properties to the system. In fact, naturally, collagen is piezoelectric, which is to say that the application of a strain allows for a voltage output, or if you apply voltage, then there is a strain that you can get out. And that is predominantly because of the presence of particular charged groups and the chirality of the molecule. So what we can do is essentially use a mechanism by which we can modify the groups on the side of the collagen to enhance this electronic ability of it. So this is just the triple helical molecule as an example. What we would typically do to it in the lab to make it a little bit stiffer, a little bit stronger, is allow it to interact with another molecule and add a little crosslink. So it's literally just holding hands for a little bit more support to weather a storm. Depending on how we choose to crosslink chemically, which groups we're incorporating, we can actually change the way in which these different charges can interact with the outside world, in this case, the cells. So by changing the charge of the collagen, we are preserving most of its structure so that the cells can still recognize most of the cues that are present on the collagen, but still find a way to essentially allow it to be either more piezoelectric or less piezoelectric as needed for our applications. So there's a bit of a chemical kind of diagram written here if you're interested, but the main idea here is just that by changing the way in which we can apply different chemistries to the original collagen, we can essentially change the charge associated with that molecule. Now, why is that important? Why is that good? Well, essentially, if we're able to link various charged groups to these structures, we can start to create more dynamic devices. So we've got examples here of essentially functionalized collagen that is able to twist and turn and bend in response to an electric field. And that can allow the creation of a wide range of devices. So a few more examples here of what the students in my lab have been up to include valve-like structures where we've got the movement of collagen with an applied voltage, just like you would get with a synthetic actuator. Also having more specific finger-like movements with the specific types of electrodes that you can use patterned onto these structures, as well as, if you can see here, there's a little bit of a pink line that moves across the entire structure. So also the potential for electrophoretic drug delivery across these larger scaffolds that we would create by applying an electric input, so by stimulating the whole structure. So in short, what could the future hold? Hopefully, with some of these technologies, my team members and I will start to look at how these can be integrated into clinical devices. So an example of this would be a compact and regenerative ventricular assist device, so a VAD for short. So currently, they're used for end-of-life patients, so they're waiting for a transplant, but you're just trying to allow them to prolong their life while they're waiting for this transplant. But they're these big, bulky devices that don't allow for much mobility in their life. So having a smaller device that allows for the pumping of the heart over time can allow for a lot better quality of life. There's also the valvular structures. Many of the structures that you saw before, where you have the structures moving up and down, can work essentially as an electrically controlled valve. And of course, integrating some of the existing bioelectronics where we have cochlear implants and other pacemakers with more regenerative components so that we can facilitate what's already there to interface a little bit better with what isn't quite there. So thank you so much for listening. I hope you've understood something new and interesting today, and I'm open to any questions that you might have.